right, looks like we are live. Give everybody a couple minutes to jump in here. As you can see, I'm wearing my Joliet Central High School shirt. No tie today. Didn't think I needed to wear a tie. I might as well take one day off of wearing a tie. So I did receive an email from a student that said there was no audio on the physics video. I don't know what happened. There was audio when I tried to play it back, but I looked on YouTube, and apparently there is no audio. So, yeah, that's definitely an issue. Oh, looks like Carla's watching me. Hi, Carla. I don't understand why my chat's not popping up here. All right, so I'm going to go ahead and I guess go through the material from the screencast that I pushed out. Again, I apologize for the audio issue. I don't know what happened when I uploaded it. I need to move my windows around here. Okay. So, yeah, hope everybody is having an awesome e-learning day. Let me back up just a second here. So what is everybody, I guess I'm just talking to Carla right now. What have you done on your first e-learning day? Oh, Jeremy's watching me too. Hi, Jeremy. So what's everybody doing on their first e-learning day? Oh man, like everybody's watching me. This is kind of creepy. Guess I'm waiting for the chat to catch up here. There's a little bit of a delay. So I really haven't done anything all day. I slept in, and I did get up at 9 o'clock though. Usually I'm at the school like super early. I did get up at 9 o'clock this morning to, yeah, you like my headphones. I see that. Did get up early this morning to make sure that everything was going smooth with everything being posted on my website. I didn't get an email from anybody until later this afternoon that there was an issue with the audio. So yeah, that's about it. So yeah, I'm excited to go through this stuff with you guys live. Hopefully you guys are all having a fun time enjoying your time off. I know doing class this way isn't as much fun as doing it live, but you know. Anyway, so anybody want to type in the chat what are we doing on our first e-learning day? My daughter's really excited to come in here and meet you guys at some point. Maybe not today though. Got to save something. Well, I guess I'll start. Doesn't seem like anybody's typing anything in the chat like what you're doing. So I'll just go ahead and get started. I'll go through my stuff, and then as you guys chime in, I'll maybe mention that as I'm going through here. Sorry, I'm not a very good streamer yet. Okay, so yesterday, or rather this morning, in the last set, I was talking about voltage. Voltage we mentioned yesterday when we were going through the circuits. Voltage is your potential difference. You've probably heard the term voltage before. Voltage is what pushes electrons around a circuit. So if you think about a pipe, it's that pressure that pushes the electrons through a pipe. All right, the unit for voltage is the volt. You've probably heard of voltage in volts before. The more voltage you have, the more current you have. So think about like water flowing. If you have a lot of pressure built up in a pipe, it's going to push a lot of that water through the pipe. So the more voltage, the more current. You can have voltage without a current. So just know that. And looks like Ariel just chimed in that, oh man, that's terrible. You had to clean the bathroom? Ugh. Need to make my kids do chores. Oh, and Sarah said, hey, Sarah, you were actually the one that sent me an email and said that there was no audio on the screencast that I did. I don't know what happened when I uploaded it. All right, let's keep going. So we talked about voltage. Let's talk about current. Current is the flow of electrons. So think about, again, water flowing through a pipe. The current is that flow that's going through the pipe. The unit of current is the ampere. You've probably heard amps before. So you cannot have current without voltage. You have to have that pressure in order to have current flow through. So pictured in the slide here is an iPhone charger. And if you look really close, sorry I don't have a very clear picture, it was hard to get it up close, but you can see that it says 1 amp right here on the plug. Okay, so that is the current. You've probably seen this before in electronics. All right, and let's move on to resistors. Okay, so resistors resist the flow of charge. Can't use the word to define a word, so I use the word hindrance. Hindrance just means that you're resisting. Okay, so it makes it harder for the flow to go through. So think about like if you're ever in a river, and why you would be in a river, I don't know. But if you're in a river and you're trying to go upstream, the current is kind of resisting you. So kind of think of a resistor that way. It's resisting the flow. And then the unit for the resistor, or resistance rather, is the ohm, and it uses that cool Greek letter omega. That's the trying to do this backwards like that, something, sure. So we've got a resistor here, and if you notice, it's got a couple different bands on here, different colors, and those colors actually correspond to, if you look at the diagram down here, the colored bands tell you the value of the resistor. Okay, so like the orange band, if you go down here, sorry, that's not orange, that's brown. Brown is a 1, and then black is a 0, and then we've got another brown band here, so yeah, that's how you read what a resistor is. And Mahogany says hi. Hello, Mahogany. All right, so we talked about voltage, we talked about current, we talked about resistance. You just need to know pretty much what those are, what the units are, because we are going to get into this awesome mathematical thing called Ohm's Law. And yep, that is George Ohm. He is so cool because he spelled his name George with only, he spelled it without an E. So yeah, kind of a cool guy. He's trying to be trendy back in the day. So he basically came up with this law that said electric current is proportional to voltage and inversely proportional to resistance. So this is his formula here. He's got, we can do this with the triangle. So normally we rate it out V equals I times R. But for Ohm's law, we can do the triangle just like we did in our motion unit. So basically at this point, I just have a couple practice problems I wanted to go through. And Saida says, hey Saida. Maybe I should send Mrs. White an email. Dear Mrs. White, Saida actually jumped in the live stream today and watched me and learned physics instead of watching Netflix. I'm so proud of you. All right, let's keep going. So I have some practice problems. They're pretty straightforward. So the first one says a speaker has a resistance of 40 ohms, or a speaker has a resistance of 40 ohms, has a current of 0.1 amps flowing through it. How many volts are supplied to the speaker? So let's see if I can do this right. I've got OneNote pulled up here, and I'm going to go ahead and work this out in OneNote. So let's see if this works. We have work. What does that mean? Oh, great. Cash money. I haven't done a single thing for class yet. That's great. Saida, you paused your Netflix to make this look good. Or to make this good. Can't promise this is going to be super exciting, but I'll do my best. Okay? Maybe I can grab one of my cats and bring it up to the webcam so you can see the cat. All right, so let's work this problem out. So let me recreate the triangle here. So our triangle looks like this. We've got a V in the top, I, and then R. So that's our triangle. And the question says, a speaker has a resistance. Let's see if I can actually split screen this so we can still see the question. Look at that, like a pro. Let's see another YouTuber do it like this. Okay. I only came for your daughter. Ooh, that's kind of creepy. Yeah, maybe I can get her to come in here. So let's go through this problem. We'll do the practice problems, and then if we have some extra time, I'll go grab my daughter. It says the speaker has a resistance of 40 ohms. All right, so our resistance is 40 ohms. And it has a current, so the I is 0.1 amps. And we want to know how many volts. Saida, I'll get her. Just calm down. All right, so anytime we're using the triangle to solve things, we are going to just cover up the variable that we're solving for, which is V in this case. So our equation is going to be V equals I times R. See, you just made it weird. Okay, we're just trying to do some physics right now. All right, the current is 0.1 amps, and the resistance is 40 ohms. So when we multiply those out on our calculator, which I know you all have your calculators handy right now, and you're going to type this in, 40 times 0.1 is what? Somebody chime in. I'll give you candy when we get back in school. Anybody? Type it in the chat. There's like a 10-second delay on this for some weird reason. What is 40 times 0.1? Anybody? I'll get some really good candy when I come back. Or maybe just to keep a list of everybody I owe candy to. I'm just going to do it because you guys are taking too long. All right, so 40 times 0.1, we're just going to move the decimal place one time. So this is going to be just 4, and our units of voltage are volts. Ah, nice job. All right, so I need to maybe write this down here somewhere. So let's see, cash money. Cash money. Oh, this is physics. Diamond, you should stick around and learn some physics. Actually, Mo was the first one to chime in, so she gets the candy. Mo candy. Yeah, I got it. Don't worry. Okay, so let's move on to the next one. So it says, find the current through a 4 ohm resistor if the voltage across the resistor is 8 volts. Saida, stop being mean to everybody. Jeez. All right. So, using the triangle, let's go ahead and cover up the I, since we're finding the current. So if we cover up the I is going to be V over R. So our voltage is 8 volts. Our resistance is 4 ohms. 8 divided by 4, anybody? Don't need a calculator for this. Anybody? 8 divided by 4 is... I'm going to have to get it really big. Saida, you don't hate it here. How can you hate it here? It's your house. 8 divided by 4, anybody? Okay, maybe it's a little bit longer than a 10-second delay. It's 2. It's 2. The answer is 2. 8 divided by 4 is 2. 2 amps. Nice job, Carla. You know what, Carla? You were the first to answer, so I'm going to write your name down. So, Carla. Saida, you are kind of mean. I'm just kidding. We love you, Saida. All right, last problem. All right, if a circuit has a voltage of 70 volts and a current of 3.5 amps, what is the resistance? So we're solving for resistance this time. On the triangle, we're going to go ahead and cover up the R. So our resistance is going to be V over I, voltage over current. Caesar, what are you doing? I'm doing the best I can. I want to see you do a better live stream for physics. All right, so our voltage is 70 volts. And our current is 3.5 amps. 70 divided by 3.5, anybody? Some of you participate more on YouTube than you do in actual class, so maybe I should just live stream all my classes. All right, 70 divided by 3.5, grab those calculators. Anybody? 70 divided by 3.5 is... Diamond, chemistry's at 130. Nobody ever listens to me when I talk in class, ever. 70 divided by 3.5. 20, Carla. I'm just going to put a check mark next to your name. Carla, you are going to clean up with candy when you get back, if we ever go back. All right, so right. 70 divided by 3.5 is 20, and we're solving for resistance, so our units are ohms. I would get really good at drawing those. It's like a little horseshoe kind of thing. Looks like this. So practice that. That's your homework for today. So that's pretty much all I had you guys do today. Just some basic math. What questions do you have? Did anybody finish that circuit that I asked you to do in class yesterday? so let's see if I can pull this up. I'm going to pull up my solution to the circuit from yesterday. So you get this bonus being on the live stream. You could actually even screenshot it and just drop it right into to your OneNote. So let me see if I can pull this up. Zorn balls. It's fantastic. All right, what did we do yesterday? Okay, so yesterday I asked you to create a parallel circuit with 2 light bulbs and a switch that turns each light bulb off independently. Okay, that was what you were supposed to have done yesterday. So let me pull up my circuit builder. Saida, the question's over. Stop chiming in. It's like 10 minutes ago. All right. Yeah, Saida, you're like way too late. All right. So I asked you to build a circuit, a parallel circuit with 2 light bulbs and a switch that will turn each light bulb off independently. So I'm going to start by dropping in a battery. Okay, and then let's put some light bulbs in here. Now remember, when we do parallel circuits, they should have 2 separate branches. So I'm going to throw some wire in here, like this. This is like the best parallel circuit I have ever made, right here. Gets like best circuit award. All right, so I'm going to go ahead and connect my first one here, like so. So there's 1 light bulb, and then I'll go ahead and connect my other one. Hopefully nothing catches on fire. And boom, there's the other light bulb. There's the answer key. Whoa, whoa, why are we talking about knocking braces out of your mouth? It's terrible. All right, so we need to throw some switches in here now because we want to control our Caesar. Caesar, tomorrow I want you to make your own live stream for physics, and I'm going to come watch yours, and I'm going to tell you how awesome your live stream is. No cap. All right, so we need to throw some switches in here. So I'm going to go ahead and disconnect this one here, and let's drop in our switch. Caesar, I'm going to write you up. I'm going to have your mom or dad or somebody ground you. I'm going to send an email to your mom. All right, let's throw in another switch here, just like this. So watch this. This is going to be awesome. There's one, and here's the other one. Okay, so your circuit should look something like this. All right, so each switch controls the light in its branch, and I can turn the lights off independently. So in your house, I said yesterday, your house is wired in parallel because, you know, like if you turn one light off, it doesn't turn all of the lights off in your house. You can control, or I shouldn't say you should be able to, like, you know, everybody's house should be like this, but maybe your house is weird. Maybe your house is wired in series, and when a light bulb burns out, maybe all the lights in your house burn out. Okay, I'm not going to judge you if that's how your house is set up. But for the rest of us, your house is wired like this. Okay, so that is a parallel circuit. Okay, what else do you want to know? I got about 10 minutes before I need to switch gears and start talking about chemistry. So you guys tell me what's going on at home. Anybody watching any good Netflix shows? I'm going to grab one of my cats. Why are the headphones on the back of your head? They are not on the back of my head. They're like right at the top. Who wears their headphones like weird like that? You guys judging me? Chemistry, Diamond, for like the 5th time. Chemistry's at 1:30. 1:30. Yeah. Someone said something about braces. Saida, I think you're on like a really bad delay because you're like chiming in like 30 minutes later. What is that? I have no idea what that is. It's probably, I'm gonna have to look that up on Urban Dictionary. I'm gonna look that up. I have no idea what that is. I'm looking that word up on Urban Dictionary. I'm gonna go with no. I don't have that. All right. Let's see what else. Let's see. So, are you done with notes so I can go back to FaceTime? Yes. Ariel, thank you for participating. Go back to FaceTime with your man. Saida, the assignment is due today, right now. Turn it in. What else do you guys want to know? Tomorrow I'll have something similar. It's going to kind of build off this. So if you don't understand how the math works, ask me questions. I can run through another example if you'd like, or if you feel like you've got it, you guys can go back to your shows. I really appreciate you guys spending the last 20 minutes with me. It's been fantastic. I can go grab my daughter if you guys want to talk to her, but I actually think she's really invested in a show. I think it's Henry Danger right now. So yeah, unless you guys have anything else, I will kind of switch gears and get ready for chemistry. Or we can sit here and talk about Netflix shows. I told you I'd stay here until 1:30. I'm here for you guys, remember that. All-American. I have no idea what All-American is. I'm going to Google that right now. All-American show. Spencer James is a rising high school football player and an A student at South Crenshaw High, but when Coach Billy Baker recruits him to join his team in Beverly Hills, Spencer's mother, Grace, and his best friend, Coop, convince him it's an opportunity he has to seize. That sounds like a pretty cool show. Go get my daughter. Mr. Clean looks good here. Thanks. Dear Mrs. White, Saida is being a bully. Yeah, she is being a bully. I don't have another mic for her. That would be the only thing. Maybe tomorrow. Tomorrow I will bring my daughter, and she can talk to you guys about, I don't know, Roblox maybe. So yeah, what else do you guys want to know? Caesar, I know, Caesar, man. You never say anything in class, but you're like trying to troll me on YouTube. Not cool, man. Where's his hair? It's there. I didn't shave last night. Like, if I get really close, maybe you can see it. It's there. Yeah. Lily, thank you for joining us. Lily, how's your day been? We're waiting for Lily to get back. Now that Sarah filled me in that there was no audio on my screencast from last night, I will go back and re-record that for those of you that want. 11:59, please. Saida, you need to get a better internet connection because seriously, like 20 minutes later, you're chiming in on things I said. Do one more example. Okay, so let's do one more example. Thank you. I'm not wearing a tie today. Just today. Maybe tomorrow I'll put one on. All right, let's do another example because I'm running out of things to say. All right, so let's do another example. Why don't you guys try to do this with one with me? So let's say you have a circuit, and let me redraw the triangle here. Okay, so here is here's our triangle, and let's say you have a voltage of somebody give me a crazy number. Crazy number. I'm going to come up with the number. You know what? It is 123, so let's say you have 123 volts. Voltage of 123 volts, and let's say that you have, I am actually wearing jeans today, okay, but shh, don't tell my boss. All right, let's say you have a current of, I am wearing Joliet Township High School, look at this, Joliet Township High School polo shirt, current of 6,879 amps. Okay, so these are absolutely insane numbers, but let's go ahead and let's do this anyway, okay? So we're solving for resistance. Resistance, if we look at our triangle, we're solving for resistance here. So it's going to be V over I. V over I. So our voltage in this case is 123 volts. And our current is 6,879 amps. 123 divided by, 123 divided by 6,879. I'm going to get my calculator. I always yell at you guys for using your phones as calculators, but it's what I've got. I left my good calculator at work. So 123 divided by 6,879. Who's got it? First person to chime in gets candy if we ever go back to school. Let's go ahead and round it to the, oh man, Cash Money, you are on the ball here. So that's 2. So I got 2 pieces of candy I owe Carla and 2 pieces of candy I owe Mo. So yeah, so if you round it to the 10th, you get 0.02. And since we're working in resistance, our units are going to be ohms, just like that, which is that Greek letter omega. Right, we've got about 4 more minutes, and then I got to switch gears because I know Diamond is waiting to do some chemistry stuff. So what other physics-related questions do you guys have for me? Look at my notes here. You guys can stick around if you want and learn some chemistry. We are doing calorimetry. I made an awesome video. Let's see if I can link the video. It's epic. Like, it's something you want to watch. It's probably my best work yet. Let me see if I can find the link for it. Oh, you know what? It's hidden. Can't even see it on my channel because I left it as hidden. Your channel. I don't know how to turn it back on. Where did my video go? My video disappeared. If there was an apocalypse, why would we need this? That's a very good question. We're in the apocalypse right now, I think. And, you know, if someone comes to your door and they try to rob you and they ask you, you know, what's the voltage, and you can answer it correctly, you're good. But if you don't know the voltage, they're going to rob you. So, yeah. So this might be a good opportunity if your parents need any electrical help. You could learn a little bit about circuits. Take that time. I was thinking maybe later this week I could take you guys around my house. Not all of it. You guys are asking for a house tour. I don't really know about that. But I could take you around and show you some electrical things in my house. Circuit breaker, how that works. Maybe we can even pop out a light switch and I can show you what it looks like on the inside. Just try not to burn my house down because I don't think my wife would like that. Saida, you are so late to the party. Man, we got to get you a faster internet connection or something because yeah, it's been like 10 minutes. Yeah, seriously, Saida, get better Wi-Fi. All right. So yeah, I'm gonna go ahead and get my chemistry stuff ready while you guys are sticking around. You're welcome to stick around and learn some chemistry, or you can go back to your shows. It's your call. If it were me personally, I would probably go back to my other shows because I feel like I'm absolutely failing at live streaming right now. Just remember, it's my first day. It's gonna get better. Yeah, Diamond, I'm getting ready. Just calm down. Man, she's on my case. You're probably the only chemist. Is there any other chemistry people in here, or is it just Diamond today? There's nothing wrong with just being Diamond. Let me see. I was trying to find that other video. Yeah, okay. Understandable. You go ahead and you hang out with your boyfriend. I don't know why I can't find this other video. Bear with me for just a second. I'm trying to pull up my chemistry video that they had to watch. It shows up here. Ah, here it is. Copy. So if anybody wants to watch, here is a link to the chemistry video. We're doing a lab, a virtual lab this week. Oh, Adeline's here. Adeline is here. So I have 2. Fantastic. Let's do some chemistry. So yesterday we talked about calorimetry, and I gave you guys this to work on, if anybody did it. So what I'd like to do first is go through one of these problems, and before we move on to the stuff that I gave you for today. So there are, let's see, there's 5 problems. Did anybody do any of these and you want me to go through one? Otherwise, I'm just going to pick one and start to work through it. They're all pretty much the same, so I thought I'd just do one. Anybody have a preference? Numbers 1 through 5. Going once, going twice. All right, I'm just going to pick one. Let's see. Today is the 17th, St. Patrick's Day. It's March, which is the 3rd month of the year, so I'm going to do number 3. Number 3. All right, let's see if I can make this a little bigger. I don't know how to make it bigger on my desktop. I apologize. If it were my computer at school, I could pinch to zoom, but I don't know. Let me see here. View. Yeah, I can make perfect. Look at that. That's what a master's degree in instructional technology does for you right there. Okay, so let's take a look at number 3. So number 3 says you have got a 110 gram sample of metal at 82.4 degrees Celsius. It's added to 116 grams of water at 22.3 degrees Celsius. The final temperature of water and metal is 24.9 degrees Celsius. The specific heat of water is 4.18 joules over grams degrees Celsius. Calculate the specific heat capacity of the metal, assuming that all the heat is lost by metal is gained by the water. So yesterday I told you when you're working these types of problems, there's a lot of information in the question. Let's take the information that's there and let's kind of divide it up into, because we've got a piece of metal and you've got water. So let's kind of separate this. So let's do the metal first. Okay, so in the question, and let me just write this off to the side. So we've got our equation. So mc delta T, and this is going to be of the metal, is equal to mc delta T of the water. Okay, so with the metal, let's list out what we have. Our M, our mass in this case, is 110 grams. The C, so the question it says, calculate the specific heat of the metal. So we don't know the C. All right, now we can find our change in temperature. So our final temperature, our TF, is equal to, final temperature is equal to 82.4. And then our initial temperature is 20, oops, let me go back here. Our initial temperature is 24.9. You know what? I've got this backwards. Okay, so it's saying the metal has a initial temperature of 82.4 degrees Celsius, and its final temperature is 24.9. Okay, so our delta T, our change in temperature, is going to be the final temperature minus the initial temperature. So our final temperature, 24.9 minus 82.4, is going to be 57.5 degrees Celsius. Okay, and that'll be negative. It's negative because it's exothermic, so the metal is transferring that heat to the water. We talked about that with the example we did yesterday. Okay. All right, now our water. Draw some lines in here so we don't get confused. All right, so our water, the mass of the water in the question tells us that the mass of the water is 116 grams. The specific heat of water is 4.18 joules over grams degrees Celsius. The final temperature, TF, is going to be 24.9. If I'm going too fast, please stop me. I have a tendency of getting so excited about chemistry that I just go way too fast. Our initial temperature of the water is what? Our initial temperature of the water is 22.3. All right, so our delta T, our change in temperature, is final temperature minus initial temperature. Our final temperature is 24.9, and our initial temperature is 22.3. So when we subtract those, we get 2.69 degrees Celsius. Okay, so notice our water has a positive value for temperature. It's gaining heat energy. So the metal is exothermic, it's releasing that energy. Water is endothermic, it's absorbing that energy. Caesar, you are welcome to stick around and learn some chemistry, or you can go back and watch shows or something. It's funny because you never say anything in class, but on YouTube, just have so much to say. You've probably chimed in more than everybody else. All right, so we're going to plug everything into our equation up at the top. Okay, we're going to plug in all of our values. Oh, one thing. On our equation up at the top, I want to put in a negative sign here. The metal is exothermic. It's releasing it, so I'm going to throw a negative in there. All right, so let's start to plug everything in. So our mass is 110 grams. We don't know our C value. And our delta T is negative 57.5. We're going to set that equal to the other side. The other side of our equation is all of the water values. So 116 grams of water, 4.18 is the specific heat value. And then the change in temperature is 2.69. All right, I know there's a lot going on here. So we can simplify the entire right side because these are all numbers. There's no variables on the right side. Okay, so let's go ahead and simplify the right side first. And then the left side, you're going to be multiplying the 110 by the negative 57.5. All right, and then you'll have a C left over. So I will give you a couple minutes to do that. I'm going to do the math myself here, and then we'll compare. 16, 4.18. Okay. So when you multiply out the right side, you get a very large number. I got 1,000, oops, that's the highlighter still. So you multiply out the right side, you get 1,304.3272. And then on the left side, you get, let's see, 110 times 57.5. I get 6325 times C. That's not what I got. So hopefully your left and your right side matches up with mine. So to get the C by itself, we're going to divide both sides by 6,325. You don't have to retract your message. It's okay. We're all here to learn. All right, so when I divide both sides by that 6,325, you get, oops. This is why having an actual calculator is a good thing instead of using your phone. 6,325. Oops, did I make a mistake? Times 57.5. 6,325. 4.32. I'm getting a different answer now. 4.18 times 2.69. When I get it, I get like 0.2 something, but when I did it a second ago, I got 0.199. I'm trying to look at this and see where, if I rounded something or if my calculator rounded something. I think that might have been the case. So, do we get that? 0.199 joules over grams degrees Celsius, or about that number. Your calculator may have rounded kind of in the middle. So I'm thinking my right side got rounded on my calculator. Yeah, that's what I got, the 0.2. So I'm guessing the calculator rounded because everything is, it's close, so it's probably a rounding issue. If you can put it all in at once, that's great. But if you can't, it's close. It's in the ballpark. We're not trying to land on the moon. Okay, so do we need to do another one of those? Caesar, are you still watching? I mean, I'm glad that you're watching, honestly. I really am, okay? I told my kids that I would take their screen time away if they were talking while I was working. So they're being extra quiet. But I can hear my daughter. She's watching a show right now. Do we need to do another one of those, or do you want to look at the stuff from today? For today, we had the calorimetry stuff from the lab. I don't know. I printed one out. What happened to it? So if nobody has any questions on that, I will pull up the calorimetry stuff from today. And we can go through some of that stuff, because this is very similar to what we're going to do in the lab this week. I'm trying to give you as much practice as possible before we get to the lab. Okay, so I don't threaten my kids. That's terrible. I just I lost OneNote. I was just motivating them. Okay. So this is what we're working on today, coffee cup calorimetry. So when we do the lab, or if you watch the video, you kind of got a feel for what you would have done in the lab if we were actually in school. So we had a piece of metal, we had some water, we heated up the metal, and then we dropped the metal into the water, and the temperature of the water rised. So the metal was transferring some of that heat energy to the water. So exothermic, the metal was releasing energy, it was exothermic, and the water was absorbing energy, which was endothermic. Okay, so on our sheet here, we've got all the data. This is the data you would have collected in the lab. This is just an example. So I've got the mass of both. Actually, this is just one. These are two trials. So just looking at one trial, so we've got the mass of the metal, we've got the mass of the water, we have the initial temperature of the water, the initial temperature of the metal, the initial temperature of the water, and then the final temperature. Now remember, the final temperature is, it says final temperature of water, but that's the final temperature of both. Okay. So yesterday in class it was saying, like, you've got the metal that's really warmed up and you've got the water, and the metal's going to transfer energy, so heat energy, so its temperature is going to go down, and the water is going to pick up some of that energy, so it's going to go up, and they reach that equilibrium point. So the final temperature of the water is going to be the temperature of both. And then down here in this table, we have a list of specific heat values for all of these different metals. And what we're going to do is we're going to try to identify which metal we have based on its specific heat. Now this sounds like a lot. It sounds like a lot of work, but it's really not too bad. Okay, so it's very similar to what we did just now with those practice problems. So let's take a look down at the bottom here. This is scaffolded in a way that we can go through it, and it kind of walks us through the calculations. If you can do this, you can totally do the lab. Okay, the lab isn't really that bad. Okay, so it says, what is the final temperature of the metal? Trial 1, trial 2. Okay, so in trial 1, let's see, let me go back up. So trial 1, our final temperature of the water was 27 degrees Celsius. And for trial 2, our temperature was 26.5 degrees Celsius. What's the change in temperature of the metal? So I'm just going to write off to the side here our initial temperature was 100. Let me look here. Oh, it's asking for the change in the metal first. Okay, so I was reading that backwards. So the final temperature of the metal was 27 degrees. The final temperature of the metal in trial 2 was 26.5. So when we started heating it, the initial temperature of the water was 100 degrees Celsius. So I'm sorry, when we took the chunk of metal and we put it into the water, its initial temperature was 100. So the final temperature is what we just listed for number 1. Okay, so number 2 says, what's the change in temperature for the metal? You guys are making me nervous. I'm getting all flustered here. All right, so our change in temperature, our delta T, is equal to the final temperature minus the initial temperature. So for trial 1, our final temperature was 20. Why do they have this as initial minus final? Okay, so it doesn't really matter which way we do this. So I'm going to do final minus initial. So our final temperature was, for trial 1, 27 degrees Celsius minus 100 degrees Celsius. So we get a negative 73 degrees Celsius. That's our change in temperature. And then for trial 2, it was 26.5 degrees Celsius minus 100 degrees Celsius. And that gives us a value of negative 73.5 degrees Celsius. Okay, so that's the change in temperature for the metal. And the metal's going down by 73 degrees and then down by 73.5. It's releasing energy, so it's exothermic. Okay, so next it wants us to find the change in temperature for the water. So for trial 1, if we go back up to our data table, for trial 1, it tells us that the final temperature of the water is 27 degrees. The initial temperature is 22 degrees. So for trial 1, it's going to be, it went up in temperature, so our final temperature was 27 degrees. And our initial temperature was 22 degrees. So that is a change of 5 degrees Celsius. And then for trial 2, our ending temperature was 26.5 degrees Celsius. And we started with 21 degrees Celsius. So that's a change of 5.5 degrees Celsius. Okay, so next it says determine the specific heat of the metal. Gives us the value for water. So we have everything we need here. Okay. We also have in our data table the masses, and down below in the question it gives us the specific heat of water. So let's put this together. So our equation, let me find a good spot to write this. mc delta T of the metal is going to be equal to mc delta T of the water. All right, so for trial 1, let's do the metal on the left side. So we have the mass of our metal, which is 50.33 grams, times C, times the change in temperature. The change in temperature was negative 73 degrees Celsius. And let's set that equal to the right side. So the mass of our water was 39.1 grams. The specific heat of water was 4.18 joules over grams degrees Celsius times the change in temperature, which was 5 degrees Celsius. Now, if it's easier for you to write these out without the units, that's fine. I know this is a lot going on right here. It might be easier to do it without the units, but just know that if you're solving for specific heat, we've got the wacky units of joules over grams degrees Celsius. Okay, so like I said, if it's easier to do without the units, do it without the units. Just make sure that you have units on your final answer. Okay, so let's go ahead and try to simplify this. So on the right side, 39.1 times 4.18 times 5, and then you've got the 50.33 times negative 73 times your C on the left. So let's do this together. 39.1 times. So on the right side, I get 817.19. On the left side, I get 50.33 times, I get a big number here, 3,674.09 times C. See if that matches up. Yep, that matches up with the answer. So C, to get C by itself, I'm dividing both sides by that really big number, the 3,674.09. So C comes out to, let's see, 0.222. And our units for C are always joules over grams degrees Celsius. So that's for trial 1. We're going to do the same thing for trial 2. All right, so for trial 2, let me scroll up a little bit. For trial 2, we're doing the exact same thing. We're just going to plug our numbers in. So we've got our equation. So for trial 2, we have our mass, which is 50.35. I'm going to do this without the units this time. Times C, which we don't know, times our change in temperature, which was negative 73.5. And then on the right side, our mass of the water was 39.452 times our C, which is 4.18, times the change in temperature, which is 5.5. All right, so let's try to simplify this out. 39.452 times 4.18 times 5.5. I get, and my calculator probably rounded this, but 907.00148. And then on the left side, 73.5. On the left side, I get 3,700.725 times C. Again, my calculator is probably rounding this. To get C by itself, I divide both sides by the big number here, my 3,000 number. And if you do that, let me see how close I am. 907.00148 divided by, actually pretty close. So even though my calculator is probably rounding this, I get 0.245 joules over grams degrees Celsius, which matches up with the answer key that I've got here. So I did something right. Down at the bottom it says find the average of the two trials. Awesome, got the same number. Find the average of the two trials, then use the table on the front to determine the identity of the metal. So when you find an average, you just add the two numbers together and divide by 2. So our average, 0.222 plus 0.245 divided by 2. Let's see here. 0.222 plus 0.245. Right, so I got, when I did it, 0.234 joules over grams degrees Celsius. Now this is the really cool thing about specific heat. Everything has its own unique specific heat. So we can take this value, this 0.234, and if we go back up to the table here, you look at the table, all of these are the specific heat values. So we want to find the one closest to the value we got. So let me go back up. I'll write out what we had. So our value was 0.234. And we can cross that one off, let's see, just kind of crossing off what's, okay, so it's probably either tin or silver. And 234 is really close to silver. So silver is probably what we've got here, okay? Tin was kind of close, but it's like really, really, really close to silver, so it's probably silver. And this is pretty much what we're doing in the lab. So this is like a dry run of the lab right here. So in the lab, I'm going to give you a metal. You don't know what it is. You're going to perform all these calculations, and then you're going to look at this table, and you're going to tell me which metal it is. All right? And that's pretty much the lab right there. You just miss out on the whole experience of doing it in the classroom. So hopefully the video was somewhat entertaining. It was under 5 minutes, I know that, so not too bad. So what other questions do you have? Is there anything else you want to go over? Tell me what shows you're watching on Netflix, how your first e-learning day was, have any issues checking in on attendance, what's going on out there in the real world. Diamond, are you still there? We have 6 people watching from chemistry, and I bet you one of them is probably still Caesar. Caesar, are you still there? I don't know if it'll tell me who's watching. It doesn't. Alright, I don't know if there's a delay or what's going on here. So do we want to do another problem? I can do another problem. Honestly, the ones from yesterday, not the ones from yesterday, but the ones from yesterday, they're honestly about all the same. So I'm just looking to see if any of them pop out where they might be tricky. You're babysitting? Babysitting's fun. If you want to come over, well, actually, you can't come over and watch kids, can you? Because we're under quarantine. Hey, Caesar, did you learn anything about chemistry today, Caesar? When you have me next year for chemistry, you are going to be all over this stuff. You're babysitting and doing chemistry. That sounds like fun. Yeah, all the ones from the calorimetry calculations, so the stuff we looked at earlier, they're all pretty much about the same. You're all finding the specific heat for all of these. I should get candy for staying in the whole live stream. Sure. Yeah. You said I'm trying to think what exactly you said. Like you said it was lame or something like that. So I don't know. You're just begging for candy now. But maybe, I don't know. It's a pretty compelling argument. I should get candy for staying in the whole stream. So I'm going to write your name down on my list. Caesar Candy. All right. Got it. Cool. Diamond, do you have any questions? Or you going to go back to babysitting? I should go play Roblox with my daughter. I think she's feeling left out. I think tomorrow maybe I'll bring her in as a special guest and she can do some physics with us or something. It's a really nice day outside. I'm waiting for the coronavirus to mutate and turn people into zombies. I have a baseball bat that I'm prepared to fight the zombies off with if I need to. I should get candy for even coming. Well, I'm really hoping that we do go back to school in a couple weeks because I've heard rumors that it's going to be like the rest of the year, which would be terrible because it's my first year teaching. And I really want to wrap up the year with you guys. It'd be super depressing if I never get to see you guys again. I have a couple seniors that are graduating. Well, I'll tell you what. So, Adeline, you bring up a good point. If we go back to school, I'm going to just make a list of everybody I owe candy to, and I'll make sure that you get it when we come back. I think, Adeline, you're only a junior, right? So if it gets really bad and I don't see you guys for the rest of the year, I'll make sure you get it next year, okay, when you're a senior. But, yeah, it would be super sad if I don't get to see some of my students again this year because they stretch it out for the whole school year. That'd be super sad. All right. Well, if you guys don't have any other questions, I'm going to go ahead and wrap up my stream. I'm going to be here again tomorrow, same time. Physics at 1 o'clock, chemistry at 1:30. If you guys have any other questions between now and then, just shoot me an email. You can hit me up on Skype. It's just nzorn@jths.org or even the Remind. All right. I'll see you guys tomorrow. Stay safe and don't eat all of your quarantine snacks now. Okay, I'm really, really fighting the urge to eat all of the goodies that I got in one day because then I'm going to starve and that'll be bad. So, all right.